So that would be an example of constant returns to scale. Okay, good. All right, I like that example. Another example of constant returns? So we do need to be a little bit careful here because you could, well, no, I'll say that. Give me another example. Yes. Okay, good. So the example here is production of corn. And so what would you say the inputs to corn production are? Seeds, land, water. That's the run of farmer, sure, so we've got some labor. Okay, so that's an excellent, that's in fact a classical example of a constant returns to scale production function is an agricultural production function. So if the inputs are things like land, seed, certain amount of labor to do the crop operations, and certain amount of water, maybe some fertilizer too. If you take all those things and double them, so if you start with 1 acre, produce a certain amount of corn, if you take all the inputs, exact same inputs used on 1 acre, and do the same thing on another acre, it's pretty plausible that it seems pretty reasonable to expect you to get twice the output. So agricultural production is a case where we often think of the constant returns to scale as being naturally constant. Okay, all right, any other examples of constant returns to scale production functions? Okay, no, really, I'm glad you asked the question. So right now what we're talking about is, sometimes we'll be more careful and say physical production. So yes, the outputs are things like bushels of corn, not value of corn produced. And ditto on the inputs. So we talk about acres of land, acre feet of water, those kinds of physical inputs are what we're talking about. We're not being economists when we characterize production functions here. Really, we're being engineers and trying to describe the technology that takes one set of things and turns it into another. So we'll add prices later on, and in the not too distant future, but not today, and that'll give rise. Then we'll put our economist hat back on. Okay. All right, another constant returns to scale example. Okay, I'm going to move on to increasing returns, and then we'll come back to constant maybe. So if so, increasing returns to scale production function is one where we double the inputs, we get more than double the output. Any thoughts? What's an example of such a technology? Okay, so what's the? Okay, so the example. So hold on. So the example here is a electricity generation. Okay, so electricity is the output, and what are the inputs? Okay, so fuel or heat. Okay, and water. That's good. Yeah, so the turbine's a piece of capital. That's fine. So okay, so what's the? No, hold on. No, actually, but share the logic you had a moment ago. So. Okay, excellent. So we have a physical example here where a proportional increase in the amount of water and the amount of heat produces a more than proportional increase in electricity produced. Okay, that's a great example. Thank you. Let me see. I want to fish for another example and maybe come back to that one. Another example of increasing returns to scale? Yes. Okay, let's hear it. So bread baking is the example. So bread is loaves of bread of the output, I guess. Okay, so we have labor. Is that right? Okay. So the inputs here are going to be things like water and flour and a little bit of yeast, maybe some salt, and some labor from a baker. If the baker can set a bunch of loaves to rise at the same time, and I suppose bake all the loaves at the same time. Yeah, no, that's right. Okay, so that might be an example. I'm going to return to that one next lecture, I think, actually. Okay, any other examples of that? Increasing returns? Okay, let's try decreasing. So for decreasing return technology, you double the inputs, you get less than double the output. Yes?
Cheese. You put in a lot of milk, and then to get a loaf of cheese.
Okay, hold on. So let's see how this goes. So the example is cheese. And what are the inputs? So that's the output, cheese, measured in pounds, say.
Yeah.
Okay. And what are the inputs?
Milk and labor.
Okay, milk and some labor, maybe some rennet. What else do we need for cheese? Okay, so if we double, you think that if we double the amount of milk, we'll get out less than twice the amount of cheese. Okay, so first of all, we should double the milk and the labor and the rennet. So why will the doubling result in less than twice the amount of cheese, though?
I guess if you were doing it by pound, like the more pounds of milk you put into production, the less cheese you get out.
Okay, so I'm going to, with apologies, use this as a counterexample. Go ahead. So the idea here is, I think, and correct me if I'm wrong, we take dairy product as an input to this technological production function, and that transforms into another kind of dairy product, which is smaller in terms of weight or volume than the original input. So that's a little bit. If the thing that was being produced was milk, fluid milk, I'd be with you. Although why we ever use such a production function, I don't know. But I think we're producing cheese here, which we want to treat as a distinct good. So the question we should ask about cheese manufacture is: if we double the amount of milk put in, double the amount of labor, double the amount of rennet, do we get out twice as many pounds of cheese as we did before, or do we get more or less? So I'm going to take this as actually, I'm not a cheesemaker, but I think this is actually probably a pretty good example of a constant return to scale production function. Yes, Scott?
What about hand-carved wooden objects? Because if you double the amount of labor, not everyone's equally skilled, so just because you double the amount of labor doesn't mean you can produce twice as many hand-carved wooden objects.
Okay, so actually I like this example. Although I'm going to use it as okay. So the example is this: we're going to produce hand-carved wooden objects, and the inputs are wooden labor. Okay, it's probably capital services in the form of some chisels or a knife, some cutting tools like that. Now, if we and the argument here is that if we double the amount of cutting tools, double the amount of wood input, double the amount of labor, we're going to get less total output than we did before. And the reason is because the first guy we hired was a really good whittler, and he was the best whittler, in fact. And so the second guy isn't as good. Okay. I like that example. I think that if we're going to be careful about modeling that production process, we want to treat the labor of the really good guy differently from the labor of the not so good guy. So this is a case where when we ask the question about increasing, decreasing, constant returns to scale, we want to make all the inputs that when we do the doubling exactly the same. So we want the really good whittlers, identical twin, whatever, we went to the same whittling school, and all that kind of stuff to really exactly duplicate the inputs we used for the first instance. Yes. Yeah. Yeah. Okay. So you're raising an excellent point. Let's see. Do I want to talk about it now, or I want to come back to that point. Okay. I want somebody to come up with a decent example of a decreasing returns to scale production functions. Yes. Okay. Rabbit farm we've got now. Okay. Let's hear it.
You get one rabbit, you only give her like a small amount of food, next thing you know, there's like 6 more rabbits.
Okay, so the inputs are breeding pairs of rabbits, some land and hutches and stuff.
They reproduce like exponentially really fast with like
Yeah.
little increase in food.
Okay, all right. So the observation is that rabbits are capable of quite rapid reproduction, and the inputs to a rabbit farm. Have you any experience raising rabbits? You have a rabbit? Yeah. If you get two, that's what triggers them. Yeah. Okay, so the observation is that the rabbits are capable of very fast reproduction. I want something. So did you intend this as an example of a decrease in returns to production? But, let me look for a different example. I'm not sure that's quite clean enough. Yes, Amir.
Would sandwich making work technically because in a confined space? Because if even if you increase all the outputs, if you're like in a store, for example, let's say Subway, and they keep on increasing the number of employees, eventually the space, like if the space doesn't increase, then they can't make the a proportional amount of sandwiches to the amount of materials they're getting and the workers they're employing.
Okay, good. So Amir says, so we had Chris earlier on say, peanut butter and jelly sandwiches are a perfect example of a constant returns to scale production function. The inputs are bread, peanut butter, jelly. You double those inputs, you get twice as many sandwiches. Amir says, oh, okay. I think that Chris forgot something. The inputs here are bread. I'm going to have Subway make peanut butter and jelly sandwiches. Okay, peanut butter, jelly. But there's also some space where the workers have to work. So there's labor and there's kitchen. And if we double all the bread and peanut butter and jelly and stuff, and even if we double the labor, the guys are going to be working in more confined conditions, and as a consequence, they're going to be less productive, and we're going to get less than double the inputs. I'm going to come back to your point in a moment. I know what you're going to say. And so that's a good example of a decreasing returns to scale production function. Okay, so that's what you were to say, right? So here's the question. In Amir's example, so Chris says peanut butter jelly sandwiches, constant returns to scale. Amir says, hey, you forgot an input because the kitchen is fixed in size, and we have several objections that say, hey, you have to double the kitchen too because we're regarding it as one of the inputs. So that's exactly right. Presumably, if you took one Subway with all its peanut butter and bread and workers and kitchens, and built another Subway with the same another kitchen and workers and in the cookie cutter way they do, you could produce twice the number of sandwiches. So that looks like a constant returns to scale production function. Okay. Now, so that brings us back to a quite general point, which is that if you view the set of inputs to a production function broadly enough, then it starts to look like all production functions are constant returns to scale. So if we were to come up with another example of a decreasing returns to scale production function, usually the reasons people give, they'd say, is because it's some factor which is fixed. And if you treat that as something which also ought to be doubled, you wind up back in a situation where you think, well, we're going to have constant returns to scale. Even you can be really broad. You can say, okay, we have a production function, and it depends on capital and labor and the finite resources of the planet Earth. And so we can double the capital and labor, but the finite resources of the planet Earth are going to lead to decreasing returns to scale. To which I would say, well, we're talking about doubling all the inputs. So what we need to do is build another little Earth over here. And if that's another one of the inputs, if we think broadly enough about that, we'll be back in a situation with constant returns to scale. Now, that's not a suggestion that it's useful to always think about all production functions as being constant returns to scale. It's not practical for most problems to build another Earth. So you sort of need to decide based on the problem about what factors are things that the firms or the producers really are capable of changing over some time scale and make sort of an intelligent decision about what the inputs are and what's going to be held fixed in the problem. Yeah. Outputs can be services too. I'm going to tend to physical examples because it's kind of easier to think about. But hold on. Okay, so I like that. So the example here is a haircutting salon. So the output is haircuts, I guess, and the inputs are people, scissors, chairs, something like that. So the question is, if you double all the chairs, workers, scissors, could you do twice as many haircuts? And you might think the answer is yes, but there's an objection, which is you might run out of heads. And well, if heads are also, you might plausibly say that input to this is people with long hair, so we need to double this too to make it constant returns to scale. Okay, yes. Good question. So let me, I think that's my prompt to turn to the next slide. Or no, actually I have, hold on, let me come back to that. Okay, so let me keep going if there's no questions about this. Do you have a question? Okay. Okay, so I want to make one little technical observation about returns to scale, which is going to be useful and provides a connection to homogeneous functions, which we've studied in a context of consumer theory. So as you might have sort of guessed from these definitions of returns to scale, there's a close connection. So in particular, if we have a production function, which is also a homogeneous function, and it doesn't need to be, but if it is, then, so here's the definition of homogeneity. If f satisfies this thing, so that we can increase inputs by lambda, we get out the same original f multiplied by lambda raised to some power. This is just the definition of a homogeneous function. Returns to scale matches up with this notion of homogeneity really cleanly if f is homogeneous, although we need to require lambda to be positive to 1. So what we need in particular is if f is homogeneous and of degree 1, then it is a constant returns to scale production function. If it's homogeneous and the degree of the homogeneity is greater than 1, it's an increasing returns to scale production function. And finally, if the degree k is less than 1, then it's a decreasing returns to scale production function. Okay. All right, so that's just a connection to something you guys already know about homogeneous functions. All right, some quick examples here, mathematical, before we forge ahead. So let's look at the top line here. So this is an example where you have a production function, 2 inputs. We just add the inputs together. So tell me, mathematically, does this thing feature increasing, decreasing, or constant returns to scale? Yeah, this is an easy one. If we double x, we double x1, we double x2, we get out 2x1, x2. So it's a constant returns to scale production function. How about this one here? So this is a Cobb-Douglas production function. You've seen utility functions that look kind of like this. If we double x1 and x2, what happens to total output? So I heard mutterings without. Let me say it again. Increasing, decreasing, or constant? Who votes for increasing? Okay. Who votes for decreasing? And here's a intelligent point, which is g. Doesn't it depend on alpha and beta? Okay. Well, yeah, it does depend on alpha and beta. In particular, you may not recall this, but the degree of this function is related to alpha plus beta. So this is a homogeneous function in x1 and x2. It turns out to have constant returns to scale if alpha plus beta is equal to 1. It turns out to have increasing returns to scale if alpha plus beta is greater than 1. And it turns out to have decreasing returns to scale if alpha plus beta is less than 1. Good. Okay. Here's another one. Square root of x1 plus x2. Decreasing. Yeah, that's good. So if you double x1 and x2 here, you're only going to get back the square root of some of those things. So this is a decreasing return to scale production function. Okay. Questions on this? Okay, so Chris asks, example involving agriculture again, where you hold land fixed, you add water. That is going to be an example of what I was earlier calling factor returns rather than returns to scale. So for returns to scale, we really want to think about doubling all the variable inputs. It would be interesting to characterize production functions in terms of how they respond when you hold land fixed and increase water. But when you do that, when you ask that question, you're not asking about returns to scale. Instead, you're asking about factor returns. Okay. All right. So here's a picture for you. I'm going to start drawing here in a moment. So I want to now sort of switch away from a discussion of returns to scale, although you'll see it's going to come up again and again, and try to think about the kind of comparisons which actually Chris's question sort of supposes. So I want to think about a couple different things here. So what I'm going to draw here, this is supposed to be an x on the, or I guess an x1 on the horizontal axis here. So I've got a production function f. It depends on the same inputs x1 and x2. What I want to do now is actually ask exactly Chris's question. What happens if I hold one of the inputs fixed, hold x2 fixed in this case, and increase just x1? And so the answer is, we're going to call this TPP, for total physical product. So the total physical product of, and there's a sub 1 here, so I'm going to ask about the total physical product of good 1, is going to result in a graph that looks like this guy. So this is the graph of the total physical product of the first input, x1, holding x2 fixed. So we're not in the world where we're doubling everything now. We're just increasing x1 and holding x2 fixed. Okay, and so this gives us a graph of the amount of output, y, that we get as we perform the experiment. Okay, so just looking at this and sort of characterizing the response, so we're holding x2 fixed at some particular level. It doesn't really say here, some level x2, I guess. You increase x1, you can see that the total physical product is increasing until we get to what point? Until we get to, I think it's probably 2, is the way I did this graph. So until we get to 2, and then it actually decreases. Okay, so we add enough x1, we start getting less y instead of more y. Okay, any an example of a production process that might have that response, where you increase one input enough, you start getting less output? Yeah. Is that right? That's, I didn't know, that's good. Okay, so Eric says, he goes back to his turbine example and says if you supply too much energy to the turbine, something goes wrong and it produces less. What goes wrong exactly? Okay, so one thing is to make the turbine explode. That would reduce efficiency. Okay, we'll leave that aside. Another example was Amir's example, where the workers at Subway started to step on each other's feet if you put too many workers in there while holding the kitchen fixed. Okay, so that's total physical product. There's also another thing I've tried to draw here, which is the marginal physical product. So this M stands for margin. That's the marginal physical product is the slope of the total physical product at a point. And so the total physical product of x1, when you take it to be 2, is about 3. The marginal physical product of x1 is always going to be equal to the slope of the total physical product curve. Okay, I want to take. Okay, so that's total physical product. There's also something we'll call yes. So yeah, sorry. This thing is ignore the thing with the x's on it. So this line here is meant to have a slope which is equal to which is tangent to the total physical product. Thanks. All right. So that's total physical product. Here's a mathematical definition of the average physical product. At this point, I'm going to draw another picture for you. So we're going to vary x1. We'll have some measure of y. We'll indicate this. We're going to hold x2 fixed. This notation with the bar is meant to indicate that the stuff on the right-hand side is held fixed while x1 varies. So we've got some production function, some total physical product that looks like this. Okay, so that's TPP of input 1 for this production function. Now so that's total physical product. So I want to now define average physical product. The total physical product is equal to f of x1, x2, but we're going to hold this fixed. We're also going to define something called the average physical product, which you can see up there. We're going to define this to be f of x1, x2, all divided by the level of input, x1 that we're supplying.